All right, everyone, we're going to get started here. We might still have a few people trickle in, but thanks for coming today. My name is Ben Wiggins. I am the program director for DASH, Digital Arts, Sciences, and Humanities. We support teaching and research that intersects with digital technologies and studies digital things. So if you're a grad student, faculty member, or anything, come see us. We have a website, dash.umn.edu, and you can find a lot of resources on there and how we can help you all with your projects and such. Today, Michael Berkowski from Web Development in the U of M Libraries is going to be leading the workshop, so I'll turn it over to Michael. Thanks.
Hi, good morning. Thanks for coming. Let's see, it's blinking green, so I'm going to assume that thing's playing. Clip it there. These always remind me, I come from I was born at the right time into the right culture for which Star Wars was really important in my young childhood. And these little microphones always remind me of the little communicators that they use when they're trying to get C-3PO to shut down the trash compactor. So I'm muted. Now it's green again. It's blinking green. I think the Empire. Yeah. You good? Okay. All right. Well, I'm going to clip it here. So sorry for that little aside. Okay. So let's see how we do today. Thanks for coming. Like Ben said, my name is Michael. I work in the university libraries. And I did not start my career as a programmer. I was a grad student in the School of Music 15 years ago. I was a music composition student, and I got involved in programming because I was wanting to learn how to generate music from code or from algorithmic processing. So I started kind of learning along the way. I was a grad student. I worked in the libraries as a student worker, and eventually got hired as staff, and eventually started introducing little programs to improve workflows in my work unit in the libraries. And more that was happening, and eventually they made that my job. And now, all this time later, I've been working as a full-time programmer at the university for 10 plus years after that initial introduction. So along the way, I learned how to do this stuff in the same way that a lot of other people working in faculty and staff and grad student positions do learn, which is just by kind of doing and figuring it out as we go. I mean, Jennifer worked with me 10 years ago and knows that back then we had as many questions as we had answers in terms of how to build stuff. So, and we just figure it out, we solve it, and eventually we get pretty good at it and pretty facile with different languages. So what I want to do today is talk to you a little bit about some high-level concepts. I wouldn't expect you to leave here today knowing how to write any kind of program, but I would hope that you could leave here today with a general idea of what programmers do, what it means to write a program, what it means to, or what are the basic building blocks of what goes into pretty much every program that's written for pretty much every purpose. We'll look at what makes up a programming language, what it is, what a few different types are, and what their purposes are, like what they're good at, what they're good for, what they're not so great for. And then I put together a couple of short lab exercises that if you've got a laptop, you can work through, and they should be pretty easy, and we'll spend maybe 10 minutes on each of them. I'm going to go back for a second, and I'm going to make that a bit bigger. You can follow along on these slides, and it probably would be it's not getting bigger. Oh well. At my website, www.berkowski.net/-code is where these slides are hosted live. So they go, there's this little compass down in the corner, and they go left and right, and they go up and down. And so I will let you know if I'm about to start traveling on a downward path as opposed to a regular, to the right path. So like I said, good idea to follow along. Okay, so let's start out. What is a programming language? Has anybody here worked with one before? Okay, a handful of you, almost half. That's great. By the way, how many of you are grad students? Many, okay. And how many are in faculty and staff positions? Or something that's like faculty and staff? Okay, good. Oh, it's about half and half. That's perfect. And how many of you have any of you ever done any type of programming for something that ended up having to be used in real life? Okay, a couple of you? Good. Okay, so a programming language is a well-defined syntax. I mean, we could invent some kind of syntax, like a way of putting together keywords and symbols, and call it a programming language, but that's not really going to work unless there is some sort of agreement amongst other people behind it. There have been plenty of programming languages in the past that did not have a very diverse set of users. Maybe they were developed in-house at 3M or Medtronic or someplace like that, and had just a core of programmers in that location who kind of had to pass down via like oral tradition how these languages were structured. Those are not used outside of those environments because they're just not known to others. So typically, if we're going to call something a programming language, there's a pretty good chance that there is, if not an official international standards body voting on how to formulate and direct it, there's at least some group of public people who have gotten together to figure out how it's going to be made standardized and interoperable. Okay, the next thing that the programming language needs to be is sort of human readable. At least understandable to the people who have the technical knowledge, who've learned what the syntax is supposed to represent. It's not necessarily going to read like prose or poetry from a book, but you'll be able to piece together what's going on with prior knowledge of how the language works. So the computer then, its job is to take the code that a human wrote in a programming language and translate it into its machine code, which is something that is not really at all human readable, or only readable to people with very deep expertise. And this is like inside of this computer here is a CPU, little square thing with tons of little copper pins on the bottom of it that was manufactured by Intel, and it knows how to do a very small number of things very, very well. It knows how to compare the voltage on these two pins with the voltage on this third pin and make a change whether this one is turned on or off. And it does that very fast. And it takes a set of instructions to be able to do that. People don't think that way, certainly not in the way that would be required to build a modern program like that. 60 years ago, programs were simple enough that the very highly trained experts building them were working at that level. Like if these two switches are on, this one is off in that sort of way. So machine code is not something that we want to deal with. Okay, the human readable stuff that's written in a programming language, we just call that source code or code, and you'll hear me use those terms. You'll hear anybody talking about this stuff using those terms a lot. Programmers often refer to themselves as coders. Okay, so there are a few different types of programming languages, and the terminologies that I'm going to use today aren't like official dictionary terminologies. They're sort of like broad classifications that I pretty much made up in order to help get these concepts across. So in case you don't hear them elsewhere, it's because I made them up. Okay, so compiled languages. These are languages that are used to build a little executable program that you can't get the code back from once you build the program. So, raise your hand if you play like FreeCell and Minesweeper on Windows starting in the 1990s, and maybe still do it this morning. I don't know if people still play Minesweeper, but I'm pretty sure people still play FreeCell. When you double click on that file, minesweeper.exe, there's no code in there that you can get at anymore. It has been compiled from code that a programmer wrote up in Redmond, Washington at Microsoft's offices and made into this little executable file that the computer knows how to run. That it contains those instructions that are sent to that Intel CPU, but you can't really get anything back out of it. And so the thing that makes that happen, the layer in between that translates from this sort of human readable code into the completely unreadable machine code, is called a compiler. Did I need to go down? Actually, I'm going to keep going. I'm going to go down now if you're following along on the slides. Okay, so these are, compiled languages are really good for very big, very complex applications. Things that require a lot of speed because there's just a lot of things going on and need to be made very efficient in order to run on, say, a simple desktop computer like the one inside this podium, in order to make it do a lot of stuff and not bog down other things on the computer at the same time. Compiled languages are really good at that. They're used when the source code that went into them needs to be a secret or needs to be like an industry, or like a protected bit of industrial intellectual property, for example. When you don't want people to be able to find it, that's why you hand them minesweeper.exe to double click on. You don't give them the original code. And so desktop applications, these slides are running inside of Google Chrome web browser on a Windows computer inside this podium. All of that stuff is written in compiled languages. So some common examples that you will probably hear of, or maybe have already heard of. Raise your hand if you've heard of at least 2 of these. Okay, almost everybody has heard of at least 2 of them. Has anybody heard of all of them? Okay, good. Maybe you're in the wrong room, or you're going to have an easy time. Yeah, sure. Okay. All right. So up at the top, C and C++. These are like C is one of the first big general purpose languages that almost everybody could use, that could run on just about any type of computer. And C++ is a sort of a later evolution of it that added a lot more features to be a little bit more friendly to programmers. C is not a terribly friendly language to programmers, but it's very powerful, and code written in it can run very, very fast. So there's lots of stuff that is still in use today that was written in the C language from 1970 or thereabouts. Below that is one C with a little pound sign, as they actually pronounce it as C#, which is a Microsoft product specific language that came about in the early 2000s. And pretty much, if you are looking at an application on a modern Windows desktop computer, it was probably written in C#. Likewise, there are web applications that run on servers. Which I won't go too far into what a server actually is or means, that are written in C# too. Okay, so below that is Java. And Java is very similar to C#, but actually the right way to say that is C# is very similar to Java. And for legal reasons, C# is a different thing. Microsoft went about trying to kind of re-implement some parts of the Java language in the 1990s and got themselves into some legal trouble and had to take a different path. But anyway, still a compiled language. Okay, Objective-C and Swift, these are used on older and newer versions of Macintosh computers, Apple Macintosh, and iOS devices, your iPhone or your iPad. Newer stuff written for those is written in Swift. Now, who remembers 1999? And you're awesome. Welcome, by the way. So 1999, we were afraid of a thing called the Y2K bug. And the reason we were afraid of that is because a lot of older systems, financial systems, banking systems, just general, the computers that ran the underpinnings of important businesses were written in really old languages, Pascal, Fortran, COBOL, a really long time ago, like in 1980 or 1975, and they were still running 25 years later. And so there was a concern at the time that the numbers, like using a 2-year date to say the year 1999 as just 99, would cause problems when that rolled over to 00. And so at the time, it was considered kind of like a golden age for programmers who came up 25 years earlier, because they still knew how to operate these things, and they were in very high demand to bring these systems up to date before the Y2K bug hit. And then it didn't, nothing really happened. Everything was fine. And that was great. We're going to run into another similar thing in 2038 for different reasons, but that's, again, a long time in the future. Don't worry about it. Okay, I'm going to head over to the right now. So the next class of languages I will kind of breeze over here are the interpreted or scripting languages. These are languages where you can work directly with the source code and tell your computer to run it right away without having to hand it first to a compiler to make that little minesweeper.exe. I would say, like I just said, you know, C# is used to, the Microsoft language C# is used on some websites. By and large, most websites are running languages that come from the interpreted family, interpreted class. And it's not to say that there's no compiler involved in these. There is. It's just that it runs at the same time you tell the program to run. You don't have to build that executable file first. I'm headed downward. Okay. So except for really big sites, the things that are like the financial underpinnings of the university, PeopleSoft, those things tend not to be written in interpreted languages. Those are large, complex applications, and so they're written in compiled languages. All right, so with interpreted languages, you can usually work really fast. If you're the programmer, you're sitting at a desk, you can make changes and run them and see the results of your changes really, really quickly. Do you remember Jurassic Park? Do you remember when, what's the character's name? Dennis Nedry, the guy who was Newman on Seinfeld. He was the programmer building the code for Jurassic Park, right? And at some point, he got up from his desk and he said, I'm going to go to the vending machines. Does anybody want anything? While my code is compiling. And it was going to take 20 minutes for Jurassic Park's code that ran all of its gates and locks and alarms to compile. So that gave him the opportunity to go and, you know, basically ruin everything for those people. He was not able to do quick development and frequent changes. In order to make the changes he needed, he had to wait 20 minutes to see them in action. So interpreted languages, though, often can't be made to run as fast and as efficiently as the compiled languages. That's why your operating system, your Mac OS or your Windows, is not written in an interpreted language. It takes there's too much work that the computer, the CPU, has to do in the meantime to translate the instructions into what it needs to do in order to fulfill its instructions. So some common examples of these: Python is used a lot on the web, not as much now as it was, say, 10 years ago, just because some other ones have sort of pushed it aside. It has really, really good support for scientific computing. The Supercomputing Institute here in this building runs a lot of stuff on Python code. The next one down, Ruby is a language that is, if you have worked in other programming languages already, is probably going to look a little weird, but it's very powerful. And it is probably the language that has done the most to push Python aside in the web space. PHP, who's heard of PHP? Anybody worked in PHP? Okay, PHP is like the, I hesitate to say this because most of my career has been as a PHP programmer. It's sort of like baby's first language of the web. It has a very, very easy learning curve. And it's installed everywhere. If you went right now to a web host like GoDaddy or DreamHost or something and just paid them their $3 a month, you would have PHP available to you right away, and the code you put there would just run. And that's why it's as popular as it is. It's pretty easy to use. Okay, JavaScript started out its life. In fact, when I made this slide 3 years ago, and there's so much more to it now than there was 3 years ago. It started out its life as the language that kind of makes things happen inside your web browser. If you click on a button and a picture slides in from the side, JavaScript did that. It's used for a lot more stuff nowadays, and I should probably update that. But we will work with this a little bit later. Okay, so even though I keep saying that these are like, these are web languages, they're not necessarily suitable to build huge complex applications that have to run fast. That doesn't mean they're not complete programming languages. They're still what we would call general purpose, in that if you wanted to, you could build a huge bank's financial system in PHP. It's just probably not a very good idea. It's capable. They're all capable of doing those things. Just doesn't mean they're very well suited to it. Sure. Oh, actually, you can go to them if you have your laptop open now. Let me go back up to the first one here. No problem at all. If you go to this URL, www.berkowski.net/-code, you can follow along. You are welcome. I'm going to slide back over. That was the end of that. Okay, I'm going to head over to the right now. Okay. I'm including here today a bit of information on markup and structured data languages, not because they are exactly programming languages, but because you will encounter them, and because I get questions about them in the same context that I would get questions about programming languages. You will use these things alongside or alongside the like interpreted languages to make the stuff that you need to make. These are the ways that you transport your data from one computer to another. These are the ways that you display the data that you collected or formatted or processed onto your computer screen. So let's start with structured data. The purpose of these is to make a structure of data, to describe what properties, what aspects there are to a set of data. You may have just come in from a field analysis in biology, and you want to make note of how many turtles you counted in the pond versus how many flies you saw land on those turtles' backs. So you could use structured data to identify those numbers within a block of text and hand it off to a computer so it knows what to do with. That's a terrible example, I realize, and it's beneath all of you who work in the sciences, and I apologize for it. So anyway, they're not really programming languages. So let's look at a couple of examples. If you've heard of XML, you probably have. XML was the preferred way to pass data around between computers on the web from the .com era of about 1999, 2000, until it got pushed out of the way by Json, which is what programmers like now. Programmers like me, we hate working in XML, and I'll show you why in a minute. Okay, so here's an XML example of a couple of books, just to show a data structure. We've got a list of books here. It consists of an opening and closing tag. It's basically the same kind of format as HTML, if you've worked in HTML. And there's a collection of them. Here's one book, and it's got some metadata. And here's a second book, and it's got some metadata. It takes a lot of typing to make this, which is why programmers don't like it. And it takes a lot of extra characters to pass it around between computers. You could have a computer compress this and send it down, but there's a lot of letters here that need to be transmitted. And all of that equates to bandwidth and speed and efficiency problems that you would like to avoid if you can avoid them. So here's the same thing expressed as JSON, which stands for JavaScript Object Notation, because it was derived from the syntax of the JavaScript languages. So here's the same thing. We're able to get rid of those opening and closing tags and reduce the number of overall characters in this by a lot. And so this is a really simple format to work with. Programmers like it a lot. More and more data is passed between computers, between websites using this format. Okay, so let's talk a little bit about markup languages and how they differ from the structured data languages. The purpose of a markup language is to describe how a document should look rather than what is really specifically in it. And so this is a way that they often do this is by surrounding text in some kind of metadata. Here's an HTML tag that makes this bold or makes it stronger, or this one here changes the color of the text that is surrounded in those span tags. So the purpose is just to describe how it's supposed to look. It happens that some of these also have rudimentary abilities that don't make them general purpose languages, but make them able to do some simple operations to move things around or make comparisons with things that edge them toward being programming languages when they're really not. Okay, so let's look at a couple of examples of these markup languages. HTML and CSS, this is the markup language of everything that's showing in your web browser, even if it's being created as you look at it by some other process. Your browser knows HTML and CSS. That's what it displays. Next one down there is somewhat newer. I guess now it's getting 8-9 years old. A simple markup language called Markdown. Is anybody working in Git or GitHub? A few of you have been. Good. Starting with some kind of modern day web services like GitHub, Markdown's gotten really popular because it allows you to write the same types of things as HTML a little bit less richly. You can't include as much metadata as easily in Markdown, but you can bring together document structures really fast with a lot less typing. It's really easy to type out and as you type it, to know how it's going to look on the page. And that makes it popular. It makes it pretty useful. If you are working in publishing and scientific literature, mathematical literature, there's a pretty good chance that you at some point will have to learn how to use LaTeX, which is a typesetting language, a typesetting markup language, capable of doing much more complicated things like putting together complex mathematical expressions using correct symbology. You can do that with LaTeX, which you can't do in plain old HTML or even easily just like typing them in a document in Google Docs. I add here down at the bottom just to kind of illustrate that this isn't always just about text and prose and academic publication. There's a language called LilyPond that has a syntax very similar to LaTeX that's used for very high quality music publication. So even music typesetting can be done in a markup language. Okay, so I put together a couple of examples that show the same basic document rendered in different types of markup languages. This one is probably the most familiar looking. This is the HTML example. It has a little bit of a header at the top that explains what the title of this document is and some other metadata about it that one wouldn't show on the screen. It has a heading that would show up as probably as like large text on the screen, and then some plain paragraph content and a bulleted list. Here's the same thing in Markdown, and this is why if you are typing these things, you might want to find a way to be able to work in Markdown instead. Instead of having to type all of those open and close tags and get everything right and in place and nested properly for this relatively simple document, you can express it in Markdown as easy as that. As long as you remember some simple things like hyphens make for bulleted lists, and underlining something like in that way makes a heading, although there are other ways to do it, and then just type paragraphs as they are, put line space in between, and everything will just come out nicely. The same thing expressed in LaTeX. You can see up at the top, there's more metadata available here. We could break things up into chapters and subchapters, but because this is oriented toward publishing, it needs to have those capabilities. Creating a list of things is a bit harder than HTML, but this is still the format that publishers often expect, and you will need to use it if you are working in that space. I did not put a LilyPond example because I can't create a text document in LilyPond. Okay, so data manipulation and analysis. Programs can do stuff. Programs can move things around on the screen all day long. I can move the mouse, and a program behind this computer is determining where that mouse is and where to show the little pointer on the screen, and that's all fine. But most of what we do has to be, or a lot of what we do, certainly in academia, is working with a set of data. You know, some data produced from research that we then need to either just give to people, show to people, or reformat, operate on, and display. And so, almost always, if you're working in a modern application, certainly for a web application, like even these slides are, there will be some data manipulation language working in conjunction. So the first one I'll mention, which is a very important one, is SQL, sometimes pronounced SQL, or maybe even more often pronounced SQL. It is the structured query language. This is the language that is primarily used for allowing an application on the web or an application on your desktop to talk to a database, pull information out of that database, analyze it, return it to the program to be displayed. And like I said, pretty much any modern website has some database powering it. All of our university library systems, of course, would depend on a database. Like if you search our library catalog, you are in fact searching a not very complicated web application in order to deliver your search, but you're delivering it to a very complicated database application that knows the right way to find and give you the most relevant results back to this more simple web application. Okay, so and this is what SQL looks like. It typically consists of that select keyword up at the top means I want to get these things. I want to get the name and the email from this place, which is a table. Think of it like a spreadsheet, a list of columns and rows. And I want to get only the ones where the course column has the value -workshop and it's for today's date. Well, do you have any questions about this before I go? Yes, you do.
So then does the database need to be structured in a certain way for the SQL language to be able to know what a column is? Let me think of a good way to answer the question. For remote people, the question is, does the database need to be structured in a way such that the SQL can know what the columns are versus what the rows are and what the values of those columns are? Working in SQL generally assumes that the person writing, this is called a query, this is a database query, the person writing the query, which is probably or possibly the same programmer who wrote the web application, already knows how the database was structured. And a lot of thought often needs to go into how you build that structure in order to facilitate how you're going to need to query it. I could, in this case, I didn't make the table, but if you imagine this like a spreadsheet, and there's a name column, an email column, and a course, and a date. And I could have made that such that instead of a set of 4 columns with many rows, I did something silly like have one column that has the word name and then a name in a second column, and beneath that is an email, is the word email, and then the actual email address. That's a structural decision that I could have made. That's a bad decision, and so it would make it very hard for me to query that database for this type of query in the way that this application needs to run. So it's generally assumed that the person writing the query understands both how the database is structured and why it was structured that way. If you're lucky, you may be working in a place where there is a person called a database administrator whose job it is primarily to think of the best way to structure this structured data for what you need, and think of the best way to query it in order to return results the quickest and using the least system resources. The university here has a data architect who works over in the West Bank office building across the freeway, whose job this is to do for the large university systems like PeopleSoft. He's in charge of figuring out how are we going to use this huge set of data that we have for all of our faculty, staff, and students, and their jobs and their pay histories and everything else, and keep it in a way that's going to allow us to both use it now and in the future in the ways that we need to. So it's just generally assumed that if you're working with this, you already know what's on the other end of it.
And that is a good answer, but also kind of what I was asking is like, so could that database be like an XML file or a JSON file? Is there a specific SQL syntax, but the database has to be?
Okay, that's an interesting question. So can the data itself be something other than like a spreadsheet looking set of columns and rows? Could it be something like XML? Could it be something like JSON? Those exist. SQL is not the right tool for them all the time. It is really oriented toward a two-dimensional set of data. I didn't want to go too far off into this topic. There are other data manipulation languages that are almost just like applications in and of themselves that could query a JSON example that has more dimensions. So in that case, we might have a list of courses, and we might have inside the courses, there might be a group of attendees, and each of those attendees might have data about their status at this university, what they do here. And all of that is contained inside of one document. The difference here is that when you're working with SQL, which expects two-dimensional tables, you would have to find ways of spreading those out amongst different tables and linking them together. So there are different applications that are intended to query into documents like that. Sure. Mm-hmm.
If you use something like a content management system, that's sort of doing both of those things, right? So you structure your data and enter it into the content management system before you put it into that system, and then it creates a web application and maybe a desktop for the database and make it show up with.
Yeah. Okay. Yes. So I'll repeat it for. So if you are working, question is if you're working in something like a content management system, the university offers Drupal as its content management system. Pretty much what's going on there. In that case, if you're working in a content management system, you are most often you are creating the content that people are going to read on screen. And not very often do you get opportunities in a system like that as a normal user of it, as not as the developer behind it, to write the code that really goes and talks to the database. And so in that case, those decisions about how the data is stored are pretty much made for you. And your job is to just feed it the block of text that is the right length and of the right type for the place you're putting it. And it sorts out, using an SQL statement, it sticks that away into the database. And so you won't get many opportunities you won't be required to write SQL yourself. Is this helping you?
Yeah, it is, right. So you get greater ease of use.
Yep.
But less control.
Yep.
Unless you're both
The developers. That's right. Yeah. And so and that's really the reason to use a content management system. That's the reason they exist, is so that you don't have to be both the programmer and the content producer, or the programmers who already have a pretty strong idea of what type of content will be needed can choose a content management system, hand it off to the content generators, and know that everything's probably going to work out fine. And only once in a great while will they have to make some other custom code that maybe needs to write some new SQL queries in order to make it work. In the libraries, it happens that we use the Drupal content management system, not the one offered by the university, but our own that we run in-house. We have a lot of custom code because we have a lot of custom use cases that go beyond just displaying information about a department, which is how a lot of places here would use it. So we have a lot of extra data that we need to show and retrieve from other places to display on screen. So you're welcome. Okay, I get a lot of questions about R. R is a data analysis language. It's sort of a program, it's sort of a language, or it's a program that you interact with using a computer language. It is capable of a lot of stuff: data analysis, display, generating graphing and plots, even moving graphics, like time-based plots are possible in R. I, unfortunately, am not at all the person to ask about how to do anything in R. But you, as grad students and faculty who may need to work with data analysis, I want you to know that R is the thing to look for, the person, the expert to look for. And I know that CLA has some people well versed in R, and I'm sure that in the sciences departments in the sciences must have people who know it well as well too. I do not. Yes, I am familiar with MATLAB. I do not work with MATLAB. Yeah, they can be used for the similar purposes. They don't look very similar, but yes, MATLAB and Mathematica and R can do similar things. So, R has gotten really popular for text mining and text analysis. In fact, we at the libraries, we get a lot of questions about that, and we unfortunately are just not always in a position to answer them. But that's where to go. In fact, I lifted this code example from the Wikipedia page on R just because they have the most simplistic get you started examples that I could not have put together easily on my own. Okay, we've had a couple questions. Do you have any more questions before we move on to something a little bit more involved? Yes, Anne. You know what? This is probably a good time to talk about that. And that was back on. That was back on this slide. Okay, so the question's about language frameworks. When I started my career, web applications were much smaller than they are today. I did not start my career like in 1996 or anything, when web applications really didn't even exist just beyond HTML on the screen. But I started out when web apps tended to be smaller single-purpose things that maybe talked to one database and did a few different things to display on screen. Back then, we pretty much built things from scratch. If I was working in PHP, I wrote all the PHP code needed to talk to the database and get back what I needed because I knew the structure of that database because I was the one who designed it. And user expectations have grown considerably since then, where web applications, what we use in our browsers, are expected to do a lot more and fill a lot more needs. Security requirements have changed, or we are aware of a lot more issues with web security than we were 15 years ago. And those are things that have to be addressed as we build a program too. So a framework like the Ruby on Rails framework, or one in Python that's called Django, or there's probably 3 dozen of them available in PHP, is a set of code that you can download and use. A lot of them are open source. Most of them are open source code that does all of that getting started stuff for you. Sets up your database for you. Just you tell it more or less what you need, what columns you need. It creates the tables for you. Gives you code to run where you don't even have to write this SQL. You just say, I need all my users who are registered for the March 31st dash course. And it translates that simple instruction into SQL, retrieves it, and gives it back to you. That's what frameworks do. And so Ruby on Rails is a very popular one in the Ruby language. It does a lot with very, very little code from the programmer. And it's well worth exploring. College of Liberal Arts, for example, runs most of their applications that they build in-house on the Ruby on Rails framework. Academic support resources who build things like the one-stop websites here, they do as well. Libraries, we don't have very much in Rails just because we have a longer legacy. The library started building web applications earlier than most other departments on campus needed to, and so we have a lot of stuff built in PHP and other languages that just were around first. So that's what application frameworks are all about. They give you a lot of code to get started and do a lot of stuff for you with very little instruction needed from you, the programmer. Any other questions? Yes.
How have you handled over your career the ever-moving, reality of what you know to do next, right? I know that's a pretty vague question. But
no, it's not. It's
your smile, I get what
yeah.
You get what I'm talking about.
I sure do.
So like, how do you know what to invest in? Because, so you say JavaScript, and then all of a sudden it's like, oh, you've got these 4 frameworks that you can learn, and they're going to make it much easier, but it's going to increase your learning curve. So, where do you end up? How have you handled that?
Okay, that is a very good question. I wish we had an extra half hour. And so the question was, more or less, things change a lot in this field, and how do we make decisions about where to invest our time, knowing that there's a pretty good chance the rug's just going to be pulled out from under us in a couple of years. This is a very real thing. Like I said on a few slides back, JavaScript a few years ago was mostly a thing that just that we used to move stuff around and maybe go get extra little bits of data into our web application. We were not using JavaScript back then to write the thing on the server that provides that data down or goes and gets it from the database. Today, that's a thing that's very popular. These things change really fast, and programmers kind of need to decide what they're building, how it needs to be used, how long it needs to be used, and who else has to work on it. Young companies, startup companies, internet startup companies, mobile app companies, often work very fast and have a lot of people working on the same set of code, and they have like the financial ability to change things often, rebuild things often. Frameworks like the Ruby on Rails framework is almost 10 years old, about 10 years old. It has not fallen out of favor yet, but I fully expect there to be a day when nobody likes it anymore and just nobody wants to use that because something newer has come. And that means that at a place like this, where like at the libraries, we need to write applications that run for a long time. We can't easily push our way into technologies that are unproven. Even if it might feel fun to do that, that's the position that we are in. It's very different from being a mobile app developer in one of the like new companies in the North Loop downtown. They're able to just move more quickly and change things more quickly than we have the time and money to do ourselves. So you always have to think about how long the thing's gotta live and how it's going to change hands from the people working on it over the years. If the same person's always working on it and just that's their job, constantly redeveloping it, then it works well to invest in new technologies. JavaScript in particular is difficult because as it's moved into these other spaces, the community using it has not standardized around which piece or which framework they want to use, and they tend to reinvent it every few months. And for me, in fact, I was, just before I walked over here this morning, I was reading an article about exactly that was titled something like, how do you, as an old-fashioned web developer from 15 years ago or 10 years ago, and you mastered PHP and Python in 2007, how do you do this? How do you even get involved in this? Because there's so much and it comes so fast. And there's not good answers on how to do it, other than that you just have to go home in your free time and invest in it. But long story short, if you're building something that has to be used for a long time, you need to consider carefully the state of the technologies you're investing in. So let's move on because I don't. Let's move on because I don't want to use up all our time. You can do programming code right now with a computer that's right in front of you. Even if you didn't realize it, you have been able to do this for the last many years just using any web browser. Your browser has tools in it that web developers use that you don't even really have to do much to expose to the rest of the world, how the code underneath looks, and you can even play around with it right inside your browser. So I'm going to move along to the right. Okay, let's go to the website. Let's go to www.umn.edu, and I'm going to go there as well. There it is. This is the current state of the, I'm going to take this out of full screen mode. This is the current state of the U of M's website. Have a look at what you see in here. Let's move this over back to here. There's an area at the top with some links to click on. It's the header. There's big video in the middle. There's some little portals that point you into other areas. And down at the bottom, there's usually a footer with a bunch more links, privacy statements, FAQs, things like that. Have a look around, see what it looks like. Let's look at what made this page what it is, what the markup that made it possible. You can probably use Control-U, that Apple symbol. I don't know, what do they call this thing now, Mac users? This used to be the Apple key, but it's not anymore. I don't know what the name of it is. Command, is that the command? They call it Command, okay. Command-U. I'm going to hit Control-U on this computer, and it's going to pop up this view source page. It's going to show me the HTML. Oh, wait a minute. That's the HTML of my slide. I don't want that. I want the HTML of the U of M site. Try that again. So up here is a big mess of JavaScript code. And here's some more JavaScript code. And here's some HTML markup that if you were to dig through this, you could probably figure out more or less what's going on. So this big mess of HTML source, they have actually done done us a favor of leaving it indented like this so we can see the structure a bit. That's not all that common anymore, but good for us. We can deal with it. We can find different things on this page. I might actually, let's see. So let's inspect something on this page. I'm going to find this logo here. I'm going to right click on it and I'm going to inspect. Your browser ought to have an option either called the same thing as this or something very similar, inspect element, something of that nature. Now, this has brought up for me a little window here of what the browser perceives this web page to be. This is how it has reorganized that HTML in order to display it on the screen. And it's put it here for us in a really handy way. I can move my mouse over here and things I mouse over turn blue or get highlighted. So here's, let's see, let's find something big. Here's this thing contains all of those links at the top, and I can expand that and mouse through here and find different elements. Somewhere in here, here's a thing that contains that video, and I could keep drilling in until I find that item itself. You can do this on any web page. And you can change things. So let's just pick something here. Let's find, let's take health and medicine. I'm going to inspect that, so it'll drop me right to where that is. Here's this link, health and medicine. I'm just going to double click in there, and I'm going to change that to pizza and bowling. And there you have it. We have a pizza and bowling link on the university's website now. And fortunately for them, the people operating this site, I did not really change it. I only changed my browser's representation of it as I'm looking at it right now. I can just reload the site, and that'll be back to health and medicine. No more pizza and bowling. So we talked a bit about what JavaScript does, what it can do in a web page like this. I'm going to go back there. I'm going to find the console tab. Can I get this out of here? I wonder if I can. Oh, no. That's not what I wanted to do. Well, whatever. Okay, that thing went away. So, are we still viewing? Are we still on the screen? Okay, good. Thanks. So I'm going to go over to the console tab, and this is a place where I can test out and run some JavaScript. I'm going to move down now. Let's just do some arithmetic. You can copy and paste these things from these slide screens right into the console, or you can type them. So I can do this little addition and get an answer. I wrote some code that I know will do some damage to this web page, so let's copy and paste that. Simply, I just wrote a little statement of code that finds that video and just deletes it from the page. And so everything else on the page shifted around. Unfortunately, I can't put it back with code unless I reload the page, but I'll reload it and get it back. We can do some even more heinous things to this website. I'm going to find the document and the body of the document and change its background color to this terrible lime green that goes against everything that university branding people would ever want to see. We'll refresh that before they come into the room. But remember, we didn't actually change any of this. All we did was instruct the browser we're looking at how to show it on the screen. Any questions about that?
So the two screens, the element is that based on like the document model, right? And then console is that a particular JavaScript console?
Yes. Yeah. Right. So this tab elements, this is how the browser understands the document to be organized. The structure, the nested structure, boxes of content, lists inside of those boxes, links inside of a list item. This is how the document is organized here. And the console is just a place for it to show output from JavaScript code, to list errors if there were any errors in the code. And it also happens that you can just run code there, and it will run in context of the page that's on the browser.
So that's why it's always just use it for debugging.
Yep, absolutely. It's a great place to debug. If this was a site that had problems, there would be maybe some red lines of stuff here that I would know I need to go look into as a web developer. Others? Okay. Okay, let's look at some basic programming concepts. There are just yes? Oh, you lost the slides? Okay. Share my screen. Let me return. Do you have it back? You have it? Good? Okay. What I really wanted to do was move this. Maybe I'll take this and I'm going to move it to this side because I will need this area less. That helps. Okay. So all of those programming languages, they have different syntax, they have different ways of expressing things, but they all work on the same basic set of ideas. There's not that many different concepts that make up programming, and you can collect those together as building blocks to build just about anything. So a statement is an instruction. It's one instruction. Do this one thing. I have here listed 3 statements that I can stick into my console, and it should give me 3 bits of output. Well, 4, but so each statement ran sequentially and gave me output sequentially in the order they ran. If I switched them around, the order would switch in my output. Console.log is just a JavaScript way of saying, just show me this text, dump it back out to me. Variables are kind of the next up bit of complexity in programming. They are a container to hold some bit of data. And it could be something as simple as like an integer number. It could be a Boolean true or false value. It could be a string of text, characters of text. Or it could be something really complicated like a representation of an automobile that has behaviors, has number of wheels, and it has the ability to drive forward or turn left and right. Any of those things could be stored in a variable. And so in this case, we have a declaration that creates a variable. We give it a value that happens to be a string of characters, and then we can do something to it. We can change it. So if I'll copy this and dump it in my console. And the output that I get is uppercased text from what I gave into it, because I asked it. I included this statement to convert it to uppercase. I'm going to clear this console so my stuff stays up at the top. Variables can be used in expressions that look something like algebra. We could create a number, we could add stuff to it, and we can store the result of that addition operation into a new variable that we can then hand to some other area of our program. So let's first describe the two of these. I said a number plus 1 equals 1, and it gave me the result 100 as output. But a number still has the value 99 because I didn't actually change it. I can do that again and create a new variable. So now I have this variable called the sum, T-H-E, not you, and its value is 100, and I can use that as many times in many contexts as I need to, and it will retain that value until I give it a new one. There are also variables for storing more complicated things, like I mentioned. I could create a collection of lists of state abbreviations for our upper Midwest neighbors here. I'm going to click this again, to clear that out. And state list now, whoops, is this list of values. I can open it up and I can see the individual values inside it. This turns out to be a really useful and powerful concept to be able to hand around collections of things. I can tell that list to give me any single element from it by knowing its index value, which is a number that points to its position in the list. So I will go and ask for state list number 2, and that's going to give me Iowa. Now, this is something that you would encounter in your lab in a bit, but I guess I'll just give you the answer now. Iowa is not the number 2 thing in the list. It says it has a number 2 listed here. It's not the second item in the list. It happens to be the third item in the list. And that's because in JavaScript, lists like this start from 0. In many programming languages, we start things from 0, not from 1. And so if I asked for state list number index 0, that's where I'll get Minnesota. It's called a 0-based array. Questions about variables? Does it basically make sense? Container to hold something, could be anything. Okay? All right. The next thing that all programs pretty much have to do in some form or another is called flow control or logic. Take some condition, some set of circumstances. If that condition is met, if those circumstances represent a truthful statement, do a thing. And if they aren't a truthful statement, do some other thing. That's the basis of an if or if-else logic in a program. So we have here, if the sum, we still have that variable hanging around. If the sum is greater than 99, we will show this output string. And if it's not, we'll show this output string. Go ahead and run that. The value of the sum, remember, is 100 still. I'll clear it, I'll paste this in. Okay, and so there's our output. It's greater than 99 because the value is 100. I could run the same thing again and say if it's greater than 101 and get the other, well, it says it's not greater than 99 because I didn't change the output string. string, but I got the else, what we call the else branch of this statement. Likewise, this one we know is false. I won't run that because we just did the same thing. Okay, now when we really get down to it, computer programming is fundamentally just the computer doing the same thing over and over again. While this computer is sitting here, it has a bunch of loops running in the background. One of them is saying, has the mouse moved? Has the mouse moved? Has the mouse moved? Okay, the mouse has moved. Change where the pointer appears on the screen by 1 pixel. Wait. Just ask again and again and again, has the mouse moved? Has the mouse moved? Has the mouse moved? Until it moves. If I go and get a set of, I display my bank statement. Okay, I go to my banking website. I display my bank statement. It goes to a database, executes some SQL code, gets back my list of transactions, and shows all my transactions until it gets to the end. That is a loop. That in the background there is a loop saying, list out the transaction, print it to the screen, go to the next one. Keep doing that until you get to the end. It's a loop. Loops are so important. You probably don't realize they're there, but they're there all the time. Every program you run is running loops constantly. Do you ever code in BASIC, like yeah? And so that probably looks familiar.
Like 5th grade.
Yeah, but you probably did this, and when I was in 5th grade, I probably wrote this with something less polite than hello world. And this is an infinite loop. Okay, this is the classic like kid programming BASIC thing to do. There's a line number. This language needs a line number in its syntax. It says print this text, and then the next statement says go back to that line. So it just does this forever and ever. It will never stop until maybe I had to hit the power button on my computer in the 4th grade to make this stop because I didn't have another way to halt it. Okay, so there are a few different types of loops. A really common one is called the for loop, which is used when you know how many times you have to run it. Okay, the syntax here on the screen, this is JavaScript syntax for a for loop, and it says for I equals 1. This is I is the thing it's going to use to count its iterations, where it is in its loop. Do the loop until while I is less than or equal to 100. So it's going to keep going here until I reaches 100. And this I++ is just is a syntax that means add 1 to that variable I. And we can run that, and we get 100 lines of output. On each line, I have the number. This is right here. This is letter I, and then a string of text. And I could make the ending number here anything, and it could just run forever. Honestly, if I wanted it to. But that's typically you would use this if you know how many times to do something. My bank statement is not using this because well, that's a bad example. Forget I said that. I don't want to go down that road. Okay, let's just take a moment to step out because I keep talking about syntax and I mentioned a bunch of different languages. Now that you've seen some code, let's look at how the same thing, this for loop, might be expressed in different languages because they can vary a lot. They're doing the same thing, but expressing it in a very different set of keywords and terms. So here's that same type of thing written in Ruby. It says from 1 and go up to 100, do this thing in this block. If you start out in JavaScript or PHP, this is kind of alien looking, but it turns out to be pretty easy to use and powerful and expressive. The same thing in Python. Again, this time we're going to ask Python to give us a range of numbers between 1 and 100 and print the line. And Python doesn't have any like brackets surrounding that statement. It doesn't have any of these things to contain this block. It does it based on how far indented the text underneath is. Okay, end of that. We still have that list. We still have state list. We know how long the length of state list is, because we wrote it, or we can ask the computer to tell us how long it is. So we can use a for loop to show all the items in it. I'm going to call a property on state list that's its length, .length, that's just going to tell me how many things are in it, and substitute that into my for loop and get the output. State number 0 is MN, state number 4 is SD, South Dakota. So the other side of this is looping when you don't know how many times you need to run it. My bank statement wouldn't necessarily know, may not know how many transactions I have this month. It's just going to show me all of them. It's going to keep running until it reaches the end. That's the purpose of a while loop. So you can give it a condition, a true or false condition, just like the if-else statement. And the while loop will run until that condition is met. So in this case, I'm saying while my input is not equal to the string done, keep asking me to do a thing over and over again. Now this one's a little bit more complicated. Let's see if this works. I haven't actually tested this. If I paste this in, okay, it's given me a prompt. Okay, and it says type something or type done, and I'm going to type just some random text and say it again, and it's going to keep asking me. You know, I can't get past this dumb prompt.
Which is why they put that checkbox.
Yeah, right. Yeah, don't ask again. Now, if I enter the text done, which is what it's waiting for here, and say OK, it's finally met its condition and exited that loop. If I never type done, it would just keep asking that over and over again, and it told me thanks for playing. We probably won't get through both labs. So we've got some time to do at least one of them, which is to run through some stuff that's not too different from what I just did on the screen, but you can do it yourself. Does anybody not have the slides up to be able to get the link? Okay, good. Everybody's got it? Good. So I've got a couple of links here on a website called CodePen where you can create and edit JavaScript and HTML code just in your browser and save it and share it with other people. So if you follow that link, we'll take you to lab 1 here. And let's move this thing down. Yours, if you first visit this, it may not look like this. There's a change view button, which I kind of liked this view down at the left here to give a column layout. I find it a little bit easier to read. And so there's a couple of tasks here that if you back up through the last 3 or 4 slides, you will probably be able to get through. If you want to, work by yourself, work together, take 5 minutes. I'll check where you are in 5 minutes, and we'll see, and we can look at some solutions. If we have time, we can do the second one, the second set of these. And if we don't have time for that, then you can certainly just do it on your own time because it'll only take a couple of minutes, and we'll wrap up for the day. So just take a couple minutes, run through these. There's 6 or 7 steps, and you should be able to find out all your answers by going through the previous slides, or just, to be perfectly honest, going to the next slide where the solutions are. And let me know if you have any questions or need help as you work. And this is JavaScript code you're writing, so you need to make it use the JavaScript syntax that the slides leading up to this have used. You will probably, I didn't say this. After you type in some code, click the run button up there at the top center to make your code execute. And you should get output on the right-hand side. Oh, okay. So if you do that settings and layout, you should be able to change layout. And the button down at the lower left of that window will. Also, again, in case anybody missed if you go to change view you can click this button down here to set it into this layout. Just makes it easier to see the output. How's it going? Has anybody gotten all the way to the end of this one? Or at least halfway? How's it going? It doesn't work. What doesn't work? Mm-hmm. Okay. So you are missing a keyword. If you go back to the slides, and back up a couple. Back up a couple more. So, oops, well, that one worked.
I got it.
So you are missing
Bar.
Yep, that's telling JavaScript make a variable.
Yeah.
Mm-hmm.
And change colors, so thank God. Now if we go here, can we run it?
I think this will probably run. There you go.
Voila. And if we didn't want it to have color, if we just wanted it to have color, we need to put.
Oh, the quotes that it shows in the console are not the quotes that you put on in your code.
Oh,
It's just showing those as output to indicate, yeah.
that is the string.
Yeah, that's just how this thing works. I would just not worry about that if you could ignore it.
Okay.
You're welcome.
We can move on to
Yeah.
The last element in an array without knowing its number
Mm-hmm.
is trying to do just like a -1.
Oh, JavaScript doesn't support that. Yeah, that's like C does, but JavaScript doesn't. You would have to say fun.length.
Like -1 or
So fun.length is going to give you 1, 2, 3, 4, 5, and you need -1, yeah, because you need element index 4. So fun dot, you take out those brackets and just -1 there, and that should give you what you want.
yay.
Wait. Yeah, sorry. So you need what you need is that inside. You need fun, and then that in brackets.
I like it.
So that's the index. Yep, there you go. That'll do it, or almost do it. That'll do it.
Close the bracket. Okay, I like it.
Okay, that's it.
Thanks.
What did you do? Let's see. That looks good. It doesn't run. What's above that? Is there anything?
Now I cut and pasted this.
Okay.
Is that it?
Yeah, so you've created it, but you haven't asked the code to do anything else with it. You haven't like try to display it with, if you said console.log save things, it should show you that list. In this, yeah, okay, this is a problem in my slide. I didn't say console.log on that one. But, so
what do I have to say?
If you, on the next, make a new line down below that one.
Below this one?
Yep, below the end of your closing bracket there.
Here?
Yep, underneath that, yep. And console.log. And then inside of parentheses.
No space?
No space.
Whoa.
Yep, that's right. That's right. And then type your save things inside there. And then run that, and that should give you some output. Okay?
Okay, so what is that doing?
That console.log just means write this to the console.
Do this thing
Yeah.
and show it over here.
Yep.
Okay, all right.
Sure.
So for this, I added my two variables together.
Mm-hmm.
And then what was the second part asking? I couldn't quite figure that out.
Okay. So you can save the result of the addition of those two into a new variable.
Okay.
So you could say like var sum of those two equals z number plus.
So it would be var sum. Is that what it would be?
Yeah. So your var sum is the name of the variable that's going to hold the answer.
Okay.
And you can do the operation of those and send it into that variable.
That's what you're saying, yeah.
Okay?
Yeah, that's simple. Oh, and then also, I think that's pretty straightforward. Commenting it out.
Yep. Okay, so basically that means like how these, I didn't even explain that, I guess. Don't worry about number 6 in case you got to the bit about commenting things out, because I didn't say it. Commenting out code means to disable it by putting some character for the language in front of it. So like those 2 slashes in JavaScript means don't run this code, or this is not code.
Okay.
So you can write something and then put 2 slashes in front of it, and it just will get skipped over.
Gotcha.
Okay.
So that's what that would mean.
Yep. Yeah. Just basically write something and then skip it. I'm going to put up the solution slide because we're almost out of time. I hoped we would have time to like really work through both of these, but I understand that you have other places to go. Did anybody feel like you successfully made it all the way to the end of lab 1? Yeah, a couple. Let's see if you had. That's very good. What was tricky? What did you find difficult? Nothing? Great. Success. Yeah. And it is. So infinite possibilities and just having no words for it. This is how we all feel when we get started. And the amount of information to be had on the internet about this stuff is so great now. It was so much harder in the year 2002. You had to go to the bookstore and buy a big, thick O'Reilly book that we would have downstairs here in Walter Library, and flip through it and read it. Even maybe read it cover to cover just to try and understand what was going on, and then piece together what you needed to build. Now it's much easier now. There's tons and tons and tons of example code out there. In fact, I'm going to go to my end slide because of that.
But that's sort of a problem too.
Yes.
It's greatly overwhelming.
Yep.
But there are also good books that help you. Like I have a bunch of Teach Your Kids to Code. So
Yeah.
I always like reference.
So here are some places that can help you get started, or even just get ideas for what you might want to do. We have a university institutional subscription to lynda.com, which is like a set of video tutorials. Lynda.umn.edu has tons of tutorials on all different programming languages, and they're really, really good. They're very high quality. I would encourage you to spend some time there. Code Academy is a website that offers like an interface similar to the CodePen one you're typing in right now. It'll say, do a thing, click run, and if it runs, it'll give you a green box that allows you to move on to the next step, and it moves you through fundamentals and gets even more complicated into some more difficult tasks in a step-by-step basis. Very, very well worth the time. Tryruby.org is a Code Academy-like thing just for Ruby, and is even a bit easier to use, it moves you along at a gentler pace even. Repple REPL is a read, eval, print loop. It's just it's a term that means like put in input and get output from the computer, just like we're doing. Does it for a bunch of different languages, including Python, which doesn't have an equivalent in tryruby.org that I'm aware of. GitHub, we have an institutional github.umn.edu that we can use for private in-house university code. And by today, just about all university departments are using it. And a lot of them are making their code available to be viewed by anybody in the university community there. There's some stuff that you can only see if you're like working on the same team. And then giant public github.com has so much stuff. If you're interested in any application, even businesses have their code on GitHub now, and you can get in there. You may not understand what you're looking at. You probably won't after just my little 90-minute introduction, but you will see how things are laid out. You will see what code looks like in different languages. You will see the conventions people use to indent things versus where they stick their SQL statements. You'll be able to uncover those things, and I think that even without a lot of experience, you will be able to, in some cases, pick apart what you're seeing. You know what's a variable versus what's a loop. Yes.
What do you like to read for, like, news about what's going on in the language? What do you read personally?
So I work a lot in PHP. I read the PHP developer listservs because they'll talk about what new features are going to be released. I spend time on Twitter, and on Twitter I follow some code organizations. I follow the leaders of some important projects like the Ruby on Rails project, and announcements come down from there on the PHP Symfony framework and Drupal CMS. Follow the leaders and the core developers on those projects, and that's generally enough for me to know what's going on in the areas that are of interest and of professional importance to me.
So if we look you up on Twitter, then we can find
you may be able to find some things. Yeah. On Twitter, I don't really anymore. I did I did a few years ago. I just they fell by the wayside, and I stopped using them. Yeah. Mm-hmm. Yeah. So, yes.
How do foreign languages go? This is all English.
Very good question. A lot of the world codes in English. Programmers often learn English to be able to do it. If you go to a site, there's a site called stackoverflow.com, which you will encounter if you are ever looking for things about code. I've been an active participant there for 7 or 8 years. You will occasionally find programmers coming there to get help. Amateurs may be posting their code in Polish, and somebody will say to them, like, if you want help with this, you're going to have to try and work through this in English, and that adds a layer of complexity. But a lot of programmers learn English in order to do it, because it is true. You note there's a correct observation that a lot of the keywords are English words, but there's also a sort of a symbology to it where a non-English speaker doesn't necessarily need to know the word variable. They only need to recognize what that concept is and know that that's the symbol that means it. So we're past time, which is I'm really sorry that we ran to the end of time. But thanks a lot for coming. I really appreciate you coming out today, and to the people who are on the WebEx as well, the people who are on the remote. Thanks. So email me, find me if you have questions. I'm happy to answer questions. You'll see me around a lot of, in this room, or not in this room, in this building, once a month there's a meeting called Code People, which is the university's programmers, the staff programmers. We get together and we have a presentation meeting every month. Please come to those meetings. You'll learn a lot. Yes, Jonathan?
Hacker lunches?
Hacker lunches. What'd you say?
The 14th is the next.
Oh, the next. So there's a thing called, the libraries host a thing, and so the 14th is one that you're putting on, or is that one of ours? Okay, so maybe you should announce that.
Every month, Dash has these hacker lunches where if you have, thank you. If you have programming questions, people like Michael and Michael sometimes will sit down with you for half an hour and work through your problem and try to give you help, get you started on something or get you unstuck. Yeah.
And that can, and I think that can be web design. It could be R. I think there are nerds there. It could be, the PHP, the Ruby, the JavaScript. I mean, I think it's beyond the libraries. It's a big, it's programming nerds and web nerds from across the university.
Yeah, so search University Webspace for Code People. You'll find their website, and a lot of these things are linked off of Code People. Stay in contact with Dash for upcoming Dash events and the hacker lunches organized by Dash. So thanks for coming. Sorry for keeping you over.